Hello everyone, I'm Jan from Stony Brook University. Today, I'm gonna introduce our work, UIWear, easily adapting user interfaces for wearable devices. So wearable devices are becoming a major growth sector for computing. It was predicted that the sales for wearable devices gonna be reach 55 million by 2020. And actually more and more people are using wearable devices to improve their lives. Let me first introduce some use cases for wearable devices. So, like, for example, the map application. While you're walking on the street with smartwatch, you don't have to use, just hold the bucket phone on your hand and just keep looking at your direction. Instead, by just glancing at your watch, you can easily get your direction immediately. You can also use your smartwatch to check your shopping list, or use your smart glasses to check your heart rate while you're working outside. So a dominant model for wearable apps is companion app. There are two features. The first feature of companion app is actually it mirrors and retailers the smartphone UI. Here's an example. This is Spotify app UI and its corresponding companion app UI. So the red boxes are the parts that are going to be mirrored on the smartwatch. As you can see, that those parts are not just reshaped to the smartwatch. Actually, the type also be converted to be compatible on the smartwatch. For example, like the image button, the pause button, actually already been converted from image button to the card image view. So there is more places to click on the smartwatch for users. And the second feature is that the user action happened on the watch is relayed to the phone. So for this example, while the user clicks the pause button on the watch, it actually doesn't do any local computing. It just relays this user action to the phone. And this phone app will respond to this action and just make it as a pause the song and then make it as a play button and send this UI update back to the watch so the watch can update in the UI correspondingly. So we did a survey on the top 100 apps in Android Wear market. So we divide those into 4 categories. The first category is the one that mirrors UI and performs no local computing. This makes up 78%. The example apps are Spotify, Weather, and the next few categories are standalone app, or the one that collects local data, or the one that performs some local computing. So in our project, we mainly concern on the first category, which makes up the most part of the smartwatch apps. So there's a problem here. Writing companion app is too tedious. As you can see, the lines of code of current existing companion app, it takes over 1,000, some are even more. By the way, we already exclude the code for common libraries. So as a result, lots of popular apps do not even have companion apps, like Facebook. So even you're a third-party developer, you want to develop a companion app for those. You have no way to do that. And we deconstruct Spotify companion app to figure out what constitute those 10,000 lines of code. Actually, the first part is for creating UI widgets, like creating UI and design and do UI updating when necessary, which takes up over 4,000 lines of code. And the next part is for network, for communicating the user data between the wearable and the phone, which takes up over 4,000 lines of code as well. The next part for data structure, that they define their own data structure. So the takeaway is, most code entangles UI design with UI management, and most development effort is app agnostic. What I mean by that is that like creating UI widgets and for network communicating, actually can easily be separated out from the core app logic. So given the difficulty of writing companion app, our UIWear goal is to easily build companion apps with minimal developer effort. So here's our key idea. Our idea is to decouple UI design from UI management so that the developer just need to specify the UI design by writing simple Metaprogram. This already has considerably lower effort. Then UIWear takes that Metaprogram and then create companion apps automatically, which performs the UI management. So I'm going to introduce the overall architecture of UIWear. There are mainly 3 components. The first component is the Metaprogram. So this is the only part that needs human in the loop. And the next is compiler, the UIWear compiler. It compiles the Metaprogram, and then to generate it to UI companion app. UI companion app is actually similar to developer written app, but it is generated by UIWear. And while you're running that UI companion app, UIWear runtime will be in charge of this. It actually relays the UI events from the wearable to phone and performs UI updates. So a very important thread that connecting all those three components together is that we are working on leveraging UI abstraction. This is the key idea. We extract the UI model, which is known as the intermediate representation, and retailor this UI model. And at runtime, the UIWear runtime will synchronize all the information at the UI layer. So let me introduce the high level of the compiler and the meta program. So this is the phone UI. Any developer, regardless whether you are original developer or third-party developer, you can write a meta program for this. And then UIWear compiler will abstract the UI from existing phone UI and combine it with the meta program. And then do UI retailing to generate the UI companion app automatically. But here's the challenge. How to abstract the UI from the off-the-shelf apps? There's a possible solution here. We can extract the UI from hardware buffer. As we all know that an app always consists of several UI elements, like play button, shuffle button, like this one. But why we combine them together and display on the hardware buffer? Actually, it is too late and it cannot be retailer anymore. What I mean by it cannot be retailer is that the UI elements cannot be converted to the compatible type on a smartwatch or wearable devices. This is actually how it works for RDP protocol. And so what we do to that? So our idea is that leveraging UI tree. UI tree is actually the intermediate representation of the UI. And most operating systems use this UI tree to represent their UI. And this is an example of the UI tree. And you can see that UI tree covers all kinds of the meta information, like their textual information or their location. And UI tree can be extracted by using Accessibility API. Accessibility API is originally designed for visual impaired. However, it is not enough by just using this, because Accessibility API does not extract image data from the UI. Like this example, we already extract the UI tree, but we want to render it elsewhere on the screen. Apparently, the image data is missing. So what we do to this? So UIWear augments existing Accessibility API to extract image data on demand. But in the interest of time, I'm gonna skip this augmentation, but all the details are in the paper. So for Metaprogram, there are mainly two steps for specification. The first step is to specify which UI elements are gonna be mirrored on the wearable. The second step is to specify how UI elements are retailored and placed. For the first part, we develop a drag and drop tool so that the user just need to specify which part on the screen you need to migrate on the other part, and then that's it, and we will take care of the rest. And for the second part, we develop an XML configurable mechanism for user to specify. So this is code, the entire code for the Metaprogram for Spotify. So after writing this Metaprogram, UIWear compiler will just parse this Metaprogram and to generate to the UI elements and UI layout, and then combine it with UIWear stub, which is responsible for the communication between the wearable and the phone. By combining those two parts together, you can generate UI companion apps automatically. So after you generate those, the UIWear runtime will handle all those. So here is the overall architecture of the UIWear runtime. There's a phone proxy and the wearable proxy keep talking to each other. They are exchanging all user data and UI update. So while the user action happened on the wearable, and the phone proxy, the wearable proxy will send it to the phone, and which will be forwarded to the watch, while it will take in this user input and do the UI updating, and the phone proxy will pull this UI updating, send it back to the watch, so that it can update in the UI correspondingly. So all those communication happen on the UI layer, so you don't need to know exactly the application logic. However, there's a challenge here. So phone operating systems, they destroy the UI and the UI tree when the application is switched to background. How we do that? We destroy the graphics tab, but keeping the UI tree active. This has no negative effect on power or performance. Here's how it works. When an app switches to background, for example, you turn off your screen, and the UI tree actually is being set to stop status. This will stop rendering on the graphics tabs so that nothing is disappearing on your screen. And then it stops communicating with accessibility so that there's no UI updating happen anymore. But what do we do here? So we set this UI tree as non-stop status, which will still keep updating the UI status with accessibility service, which catch this UI tree and synchronize it with the UIWear. Please notice here, it still stops rendering on the graphics tabs for saving power. For implementation, we mainly focus on Android ecosystem like Android phone, Android Wear smartwatch, and Sony smart glasses. And we pick up 20 smartwatch apps from the top 150 apps from the Android Wear marketplace based on their different category and popularities. And we mimic their functionality and look and feel by writing simple Metaprogram and generate those 20 UI companion apps correspondingly. So this is a snapshot of some of those apps we generate and their original version. So for evaluation, we're comparing the lines of code between the UI companion apps that we generate and the companion apps. So we count the lines of code of the Metaprogram, which covers all the activities. Here's a subset result. The remaining result looks similar. Here you can see that in Metaprogram, it takes less than 100 lines of code. But for companion lines of code, it always takes over thousands. So the takeaway is, UI companion apps require an order of magnitude fewer developer-written lines of code. We're also comparing the energy consumption between the UI companion and the companion on the watch. So here's the figure. The x-axis represent the name of the apps that we use to measure, and the y-axis is the energy consumption. So which means that the lower the better in this figure. So you can see that in 90% cases, UI companion apps consumes less power than the original version. Why is that? Because that we're offloading all the computing to the phone. We've also done other set of experiments to confirm that UI companion apps have comparable performance in terms of energy consumption on phone and CPU latency. We've also conducted user studies. We asked 20 subjects questions about their look and feel and functionalities by comparing those two versions. Since this is A/B testing, the subjects had no idea which version they were actually interacting with. So from this table, we can see that for functionalities, 78% of subjects think that UI companion apps is better or equal to the original version. And 74% of subjects think that our version is better or equivalent to the original version in terms of look and feel. We also measure the time it takes to write a Metaprogram for those subjects. Those subjects are ranging from novice programmer to more advanced programmer. They are including like non-CS major and CS major student, and undergrad to graduate students. So, and it turned out that on average, each subject created a working Metaprogram in less than 16 minutes. We've also done other evaluations that figured out that keeping the UI tree active in background does not affect power or performance. And UIWear can be used to create apps that on smart glasses and for creating third-party companion apps. The conclusion. We contribute a new design point that decouples the application logic and UI design. And we provide a much easier way to generate a UI companion app with few lines of code by using Metaprogram. And the UI companion app has comparable performance and power. Here's a link to our website and the link to our code repository. Thank you.